Greetings, this is Rick Powers from Western Technical College, Basic Statistics. Lesson 20, Normal Distribution, Part 2. Now that we have some background on mathematics of the normal distribution, it would be good to have some specifics in mind about describing it. These descriptions are important for later understanding of the use of this type of data. Number one, the curve is symmetric. It's the same on the left and on the right. Half of the data is below the mean and half is above. Number two, most of the data is in the middle. Number three, there are tails. As we move away from the mean, the amount of data decreases but stays as a small amount. One symbol that is used in statistics is a z-score with a subscript. Many students have not seen such a thing, so it is important to know what it is and what it is not. A subscript is a small symbol written a bit below a regular letter. For example, if I have z with a subscript 0.04, it will look like this. We are not doing any mathematics with that number. It is just a label on the z. There are many textbooks that use the subscript to indicate the z-score for a specific area of the right tail. Again, the example would be that z sub 0.04 is the z-score with an area for the right tail of 0.04. From the earlier notes, we know that is about 1.75. So z sub 0.04 is equal to 1.75. At this point, it's time for the big reveal. Z-scores can be used to transform any bell-shaped data set into the standard normal distribution. You may have seen this before. Z is equal to a data value minus the mean divided by the standard deviation. So if we have bell-shaped data, now we have the tools to predict how much data will be in any part of the distribution. However, we have to navigate a bit of statistical tradition along the way. It used to be really important, like 5 years ago, to find z-scores because the tables that were used to get probability were all written for z-scores. But now all of our technology can automatically figure out areas for any bell-shaped data set. Let's do some examples to make it clear. Consider the height of 3-year-old boys to be bell-shaped with a mean of 38 inches and a standard deviation of 1.6 inches. What percent of boys will be taller than 40 inches? In the past, textbooks would require you to find the z-score that corresponded to the 40 inches, then use a table to figure out the area. But now we can just change our graph in the technology by putting in the new mean and standard deviation. Here's what the graph looks like without finding the area. Notice that the mean, 38, is in the middle. With current technology, there's no need to be concerned about the z-score. Just put the 40 as the data value of interest and make sure the inequality is in the correct direction. The answer could be written like this: probability that x is greater than 40 is equal to 0.1056, or about 10.6%. As before, we also would like to start with a percent and find the data value to match. Example, what height will be the cutoff for the top 1% of 3-year-old boys? Or we could say find x1 so that the probability that x is greater than x1 is equal to 0.01. The answer, x1 is about 41.7. There will be still some situations where finding the z-score will help us understand the situation. But when we're working with area in the normal distribution, it's easier just to use the technology with the proper mean and standard deviation. Remember, for questions about the z-score, use the mean of 0 and the standard deviation of 1. End of lesson 20.